All right, so we're going to introduce some concepts today. We're actually not going to design any circuits yet. We'll introduce some concepts that you have to understand and you have to be comfortable with before we can then start designing circuits and getting you to see, okay, well, what is resistance? How does it actually relate to charge moving through a wire? And so before we can do that, I need to introduce concepts of charge, moving charge, voltage. Some of these, you may have had in other classes, depending on whether or not you've talked about action potentials and electric potential at all. So as we do this, hopefully we'll get a good foundation from lesson 17 so that in lesson 18, when we start really designing some more complex circuits, you have a good understanding of what's going on. But let me pray for us, and then we'll get started. Father, thank you for the opportunity that we have to study physics, Father, and to learn about how electricity works, and to learn about what we can do knowing that and how we can build circuits. But Father, so much bigger than that, I thank you that as we study physics, we get a greater appreciation and an understanding of how complex your world is. Father, that we can gain a better understanding of you. And I pray that that would happen. And as it does, Father, I pray that your Spirit would draw us into your presence, that we would grow closer to you in our understanding and in our desire to serve you. We ask this in the name of Jesus. Amen. All right, so, lesson 17, some introductory ideas. First question we need to address is this one. What carries charge? What actually is going on when charge is moving? First of all, we have this concept of what's called current. And so when charge is flowing through a wire, we say that there is a current in that wire. And so what current is it's just a movement of charged particles through a particular wire. And so we can measure current, we can describe what it actually is, and there are a lot of important ideas behind this topic of current, and we'll talk about those. So most often what's actually moving in a wire carrying current are electrons. Electrons are negatively charged mobile carriers. And what we mean by a mobile carrier is that they are moving, that's the mobile part, and a carrier, they are carrying charge. Because they are negatively charged particles, as they move, they carry charge through the wire. And so, right off the bat, you should be starting to think about something, keeping in mind that if there's current moving through a wire, and that current is almost always going to be electrons moving through that wire, you ought to be thinking about, okay, well, what is the source of those electrons? Okay, where are they coming from? And how do we continue to keep that going so that that flow can be uninterrupted? Especially thinking about items that need continual power. So keep that in mind. We can quantify the amount of current in two ways. And to actually quantify a concept is really powerful, because then it keeps you from just explaining things comparatively. Like saying this has more current than this. Well, that's fine, but until you can actually quantify it and come up with a value, all of your analyses are comparative. It's like more or less, bigger or smaller. But quantifying something gives you some real power, gives you some real ability to describe what's going on. And so if we want to quantify the current, we can do it in one of two ways. One, we can just quantify it by the amount of charge measured in coulombs flowing past a point in a given second. So Coulomb is the unit of charge. We tend to talk about current then in the amount of charge that flows past a particular point every second. Why do we use second as the interval of time? Well, second short enough that it's not burdensome, but it's long enough that it's actually meaningful. If you're talking about the amount of charge running by something in a millisecond, it's not really meaningful. Or if you're talking about the amount of charge running past something in an hour, that's meaningful, but it's burdensome. And so seconds a nice unit of time. Plus, seconds happens to be the SI unit of time. So it tends to be, in many ways, what pops up whenever time is involved in some kind of a concept. So we have this formula here to do just this, to quantify current in terms of the amount of charge flowing past a point in 1 second. So here, let's get the pen. Here you've got your amount of charge per second. So Q is the amount of charge in coulombs. T is the amount of time in seconds. And therefore I is current. We are quantifying current in terms of the amount of charge moving past a particular point every second. And so this describes how we quantify current, but in order to demonstrate what current actually is, we need to look at this concept of what the unit for current. So we tend to represent current in amperes, and 1 ampere or 1 amp, if you want to shorten it, or 1 A is equal to 1 coulomb per second. So again, 1 amp is 1 coulomb per second. So that's one way we can quantify current in terms of just the amount of charge passing by a particular point every second. Another way we can quantify current is to do it as the number of electrons passing through the wire or flowing through the wire. What's that?
Isn't that 3 ways?
So no, because this right here, the amount of charge, both of these, these are just describing how you would determine current in terms of the amount of charge. Now, in order to do the second one, the amount of electrons, you usually have to do the first. You have to figure out the amount of charge moving through at any second and then convert that number into electrons. Okay? So you may think it burdensome to use the second way, but the nice thing is that provides some meaningful data, right? Not that charge doesn't, but in terms of putting in terms of the number of electrons, it actually allows a nice connection between thinking about moving charge and thinking about the source of that charge. And so in order to do that, you have to know that the charge of a single electron is equal to 1.6 times 10 to the minus 19 coulombs. Okay, so to get a coulomb of charge, you need an enormous amount of electrons, right? If each electron has a charge that is roughly equal to 10 to the minus 19 coulombs, you need 10 to the 19 electrons to get 1 coulomb of charge. And 10 to the 19, that is an enormous number, right? And so now when you think about this charge carried through a wire, and you think about the enormous amount of electrons it requires to do that, now some things make some more sense in terms of why electricity costs what it does, why batteries cost what they do, because you need to have an enormous source of electrons to be able to move through whatever your system is, whatever your circuit is. All right? Any questions so far on current or what's actually moving? Cool. So, by the way, when you look at this video, you'll notice that I didn't deactivate presenter view. So on the screen, what you're actually going to see when you look at the video, there are going to be two screens, one smaller of what's projected up here, and then one of showing what's coming next. Sorry, I forgot to deactivate that before I actually started the video. Did you have a question with me? Okay. So this is just an illustration of what we mean when we talk about current. So here's a particular point. In this case, we can measure it with some, area, some cross-surface area. But usually we just, pick a single point in that wire and then measure how much charge is moving past that point every second. And so here's an illustration of that moving charge. It probably would be best if they would have went in this diagram put in a negative Q for all of these, illustrating that we are representing electrons, because that is most often what's on the move when you're talking about current. Although in living organisms, at least in our bodies, what usually moves when currents are moving through our body are actually positively charged items instead of electrons. But that's for a whole another class when you're talking about action potentials. So the other question we need to deal with before we spend some time today introducing Lab 7 is this question of what is voltage? So we talked about amperage or amperes. That's the amount of current, the amount of charge moving past a point in a single every second. But voltage is a more common concept to interact with when you're talking about electricity. And so voltage is the potential difference across a circuit. So it's set up by an energy source. That energy source could be batteries. It could be an outlet in your home. It could be, 7,000 oranges all strung together to give you enough voltage to charge your phone. Have you all ever seen that video? There are several of them, YouTube videos that were made a few years ago of setting up oranges to actually charge an iPhone. And I think it took like 500 and something oranges to get enough voltage to actually charge your phone. But that was pretty cool. So voltage inside of homes is usually equal to 110 to 120 volts. A typical outlet should be somewhere around that, a 110 to 120 volt, which means that the potential difference set up by the power source for that outlet is 120 volts. That is the potential difference between the positive source and the negative source, or the positive terminal and the negative terminal, or the positive node and the negative node. This all start to make more sense next week when we talk about circuits in more detail, is 120 volts. But for some things you need more voltage, like to run an electric dryer or to charge an electric car, or sometimes if you have a really old refrigerator, to power a refrigerator, although most refrigerators that are less than 20 years old can run on a normal outlet, require a 220 volt power source. Greater potential. But keep in mind, what we're talking about with voltage is not the amount of charge moving through a wire, right? It is electric potential. So it's basically the difference in charge between the two nodes, but it is not referring to how much charge is actually on the move. Now, voltage is directly related to current. What does it mean if two items have a direct relationship? When one goes up, so does the other. When one goes down, so does the other. Voltage and current are directly related. And here is the formula for voltage. So voltage is equal to I times R, where V is voltage. Again, it's the electric potential, the charge difference between two nodes. I is the current, and what is current again? Yeah, the amount of charge that moves past a point every second. And then R is resistance, measured in ohms, abbreviated with the Greek letter omega. So we'll discuss resistance more next week, but right now you should see that resistance as long as resistance remains the same, if you increase current, you're going to increase the amount of voltage, and vice versa. If resistance remains the same, if you increase voltage, you're going to increase the amount of current. Okay? So think about these concepts for a little bit before we start solving problems together. If voltage is electric potential and current is the amount of charge moving through the wire every second, which one do you think is more important when you're talking about the potential danger associated with? So voltage, so there's a volt for voltage in terms of potential difference. So if you talk about something being like, a 12-volt battery, right, used in cars. And then you have 9-volt batteries used in, like toys, right, and used in smoke detectors. Almost every smoke detector still made uses a 9-volt battery. And so the voltage difference is not that great between a 12-volt and a 9-volt, right? It's only a 30-something% increase, and yet you have a vastly different energy requirements, right? Or current, where you have the amount of charge actually moving through. And you have to keep in mind, both are important. Both are very important when you're talking about the potential dangers associated with electricity moving through a wire. But there's one of those that is particularly important. Yeah. Current. So we've got a vote for current, and we have a vote for voltage.
Well, you describe voltage as the
potential difference. Mm-hmm. Yep, so the electric potential, which you could look at as, absolutely, as a potential. So if you've got electric potential, you have the potential to turn that into energy, right? Mm-hmm. Energy that can be used to fuel something. But you have to keep in mind that current, that is that. In essence, that is what's going on. So voltage is the potential to create flow, right?
But if you want to calculate the potential, then you should calculate all the potential, even when it's not.
Yes, absolutely. Absolutely. Yep, absolutely. And that's, when you're talking about voltage, you are looking at the capabilities of your potential. But current gives you something of what's going on even with the resistance that's already in place. And so a lot of this question will become, the way to best address this question will become clearer as we look through and we actually start designing circuits and we talk about resistance and what that actually means and how it resists flow. But yeah, if you want to look at it this way, voltage it's the potential to move charge. Current is actually that moving charge. And so you can have a really high voltage, but a really low current. And so you have a great potential to move charge, but you're not moving very much of it. So the dangers can be really low. And then you can have a smaller potential, but you're moving a lot more of it. And so you can have a much higher potential for harm. And that's where you can get things like where you have a 9-volt battery, that you can touch both terminals on your tongue, and it gives you a very minor zap. I'm not encouraging you to go and lick a 9-volt battery. I'm just saying it can be done, and it gives you a noticeable but a minor zap. And yet a 12-volt battery is enough to power a cattle fence several meters long that will keep cattle from wanting to rub up against it, because it is a very significant zap that you get in touching those charged wires. And where the voltage is not all that different, but there's a major difference in the amount of current that's allowed to flow. So yeah, both are important. Both voltage and current are important in assessing the potential dangers. You have to keep in mind, but current is the amount of charge that is actively flowing, that's on the move, that has a potential to be, deposited into your tissues. All right. Are there any questions about current, voltage, what they are, how they work, before we go and solve some problems? Okay. So let's see if this. Oh, cool. It's actually going to work. So how much current passes through a circuit if 65.2 coulombs of charge passes by a point each minute. You see what I did there with our unit of time? Note that it is not seconds, it's in minutes. So first question, what do we have or what are we given? So we're given that charge, Q, is equal to 65.2 coulombs, right?
We have to change the minutes to seconds.
Yeah, so we're given that time is equal to each minute, so time equals 60 seconds, right? There are 60 seconds in every 1 minute. Bless you. So this is what we have, or this is what we're given, that our charge is equal to 65.2 coulombs, and our time is equal to 60 seconds. All right, tools. What tools do we have to solve a problem like this? We have that current is equal to Q divided by T,
Square.
right?
T squared.
It's just T.
Oh, I wrote it wrong.
And so what do we want? We want current. So our tool is already in the right form. Current, or I, is equal to charge, which is 65.2 coulombs, divided by 60 seconds. And remember, a coulomb per second is equal to what unit? An amp or an ampere? Okay, so we can, since we're going to set up now with coulombs divided by seconds, we can convert that into amperes. So our units will be amps or amperes, and we should have something equal to 1.09. 1.09 amperes, or 1.09 amps. Let's clean that. I guess that didn't really clean up that circle at all, but hey, 1.09 amps. And so that's how much current passes through a circuit if 65.2 coulombs of charge passes by a point each minute. So 1 amp. And 1 amp, that's a very common current. 1 amp, 2 amps, 3 amps, those are very common currents. Keeping in mind that each coulomb is 10 to the 19 electrons. Okay, so even in 1 amp, you are talking about an enormous number of electrons that need to be separated from something, that need to be generated from something. And so usually, a lot of it is generated by getting water to turn a turbine, right? And so in that, you create like static electricity, you heat up steam, you get a source of electrons, and you can then use those and move those through. All right?
I just have a quick question just about, I think there was a typo or something a while back, because when you're referring to it, you're saying 10 to the 19, but I thought I read it written 10 to the negative 19.
Yeah, and so that's electrons in terms of charge. Each electron is, 1.6 times 10 to the minus 19 coulombs.
Yeah.
And so then if you wanted to go the other way and to say how many electrons are there in 1 coulomb, then
Yeah.
you would end up
Okay,
getting that 10
sorry.
to 19. No, that's fine. You don't need to be sorry. Yeah, I transitioned in how I was describing it without any methods for showing you, so it's my fault. I'm sorry. But we'll actually do that right now. In the next problem, I'll demonstrate to you how to make that transition, which maybe I probably should have done before I started talking about it. So are there any questions here? This looks confusing, so I'm going to make this obviously an I, because it looks like a 1. So I, or current, is 1.09 amps. All right. So our next question. How much charge passes a point each hour if the current is 2.00 amps? So what do we have, or what are we given? We have current, I, is equal to 2.00 amps. And we have time is equal to, again, we want this in seconds. There happen to be 3,600 seconds every hour. Anyone disagree? It's actually not in this problem, it's in the next one where we deal with it. I forgot I added another problem in which we were solving for a different variable. So 3,600 seconds in an hour. Are all of you okay with that without seeing how it's worked out? Mm-hmm. Okay. So then tools. So we have the same tool as before. Current is equal to charge divided by time.
We're solving for Q.
Yep, and we want Q.
So it'll be I times T.
Yeah, so we're going to rearrange this to solve for Q. So we'll multiply T to both sides. T will cancel out here, and we get Q is equal to I times T. And so Q is equal to I, which is 2.00 amps. Now let's go ahead and change amps into what those units actually mean. What is 1 amp? C over S. And then we're going to multiply this by 3,600 seconds.
S's will cancel it.
Yep, so the S's will cancel. And we will get that Q is equal to 7,200 coulombs. And now this is a little bit interesting, significant figure-wise, because I guess we only presented this with 2 significant figures, so that's fine. We can leave our answer like that with 2 significant figures. Although, technically speaking, since 1 hour equals exactly 3,600 seconds, that should not limit our number of significant figures. So technically speaking, we should present our answer with 3 significant figures like our current value had. And then, so in order to present this with 3 significant figures, you would need to do 7.20 times 10 to the 3rd power. That would be the only way to present it with exactly 3 significant figures. Unless you wanted to do 72.0 times 10 to the 1st power, but that would be silly. Because if you're going to start go to scientific notation, you got to commit. 7.20 times 10 to the 3rd power. Okay. But we'll leave it as 7,200 coulombs. Is that all right? So again, relationship between, now the relationship between current and time is an inverse relationship. Okay? The relationship between current and voltage is a direct relationship.
So on a test or homework, if we do it where we count the sig figs for the time, like 3,600, will we mark
This one I would say was okay, because since you presented this with 2 significant figures, I would allow you to present your answer with 2 significant figures. I just want you to know that technically speaking, since 1 hour is exactly 3,600, that does not need to limit your number of significant figures. But yeah, if you presented that on an exam, that would be fine. Okay, now we get into converting from charge to electrons. Okay, so how many electrons pass a point each second if the current is 3.00 amps? And remember when we were talking about this before, I told you that if you're going to quantify current as the number of electrons, you have to first determine charge, and then from there determine electrons. So it is a 2-step process. It's not so clean as to do electrons per amp. All right, so what do we have? We are given time is 1 second, right? Tells us how many each second. So it's nice this problem didn't give us minutes or hours. And then we're given current is equal to 3.00 amps.
Do we want to put it in C over S though?
Yeah, we'll do that when we start working through that. We'll change amps into coulombs per second. And you're like, well, why don't we just leave current always as coulombs per second? That is an excellent question. Why don't we? I don't know. It's a similar question to, asking, why don't we leave, I guess we haven't introduced this yet, but we will. Why don't we leave, joules per second as joules per second instead of changing it into watts? And it's because we're talking about a different concept, and so it can have its own units. So tools, we're going to use the same tool. Current is equal to charge divided by time. But then we also need that the Q of a single electron is equal to 1.6 times 10 to the minus 19. Oh, I'm running out of space. Let's do this again. 1.6, I'll erase this, times 10 to the minus 19 coulombs. Okay? And then what do we want? We want number of electrons. But we can't solve that directly. Right? We can't solve that directly, so we want the number of coulombs, and then from there we can determine the number of electrons. Does that make sense? So this problem is like the one previous where we're solving for charge, the number of coulombs, and so we'll use our modified tool where charge is equal to current times time, so 3.00 amps, which is coulombs per second, times 1 second. Yes, yeah. Sorry, I'm writing with my finger because I didn't know if this was going to work, so I didn't bring my stylus. And my finger is significantly larger at the end than the stylus is. All right, so we are also dealing with 3.00 coulombs, right? Seconds cancel, and 1 times 3.00 is just 3.00.
But would you want it to be 3 because of the 1 second?
Yeah, I guess we could, but again, you've got the same issue here that we're talking about. It's exactly 1 second,
Yeah.
or it's implied to be exactly 1 second, so it does not have to limit your number of significant figures. But again, if you decided at this point to say to limit it to 3, I would be okay with that, and then to present the rest of your answers with 1 significant figure, that'd be fine. All right. So the number of electrons, I didn't give you this tool before, but the number of electrons is going to be equal to the charge divided by, so actually we'll do Q, divided by Q of a single electron. Right? And that's where we get what I was doing before of just, converting straight from charge of an electron into the amount of electrons in a single coulomb. I didn't actually go through this process. I should have introduced that tool previously. So if we want number of electrons, so the number of electrons then, which is actually what we want, number of electrons.
1, 2, 3 divided by 1.6 times 10 to the
Yep, equals 3.00 exactly coulombs, or if you limited it here to 3, then it would just be 3 coulombs divided by 1.6 times 10 to the minus 19 coulombs. And coulombs will cancel, and you'll be left with just a number, which is good, because if you're talking about the number of something, it should be just a number. And so 3.00 divided by 1.6 times 10 to the minus 19.
With 3 suffix, it would be 1. Yeah, but with 3 suffix, it would be 1.88 times 10 to the 19.
1.88? Okay. 1.88 times 10 to the 19.
My calculator still has this negative 19.
Yeah, because if you divide it by a negative exponent, it should have popped it up to the top
Yeah.
and switched the signs.
Yeah, I know, but I don't know why it didn't do that.
I'll take a look. You might actually have to put that in parentheses when you do the exponent to make sure it's not adding the negative 19 after it does the division, which is probably what it did, is it did the division and then added the exponent afterwards instead of putting the exponent in on the denominator. Okay, and so again, if here you decided to limit your charge to 3 coulombs because you had 1 second and you didn't consider it to be exactly 1 second, then you need to present your answer in 2 times 10 to the 19 electrons. But this is a huge number of electrons. So You just keep that in mind when you're thinking about amperage and you're thinking about current. You're talking about an enormous movement of electrons. Now, electrons are very tiny, but still, you're talking about a big process. All right? Any questions? That okay? So far? Cool. All right, next question. How much current is in a wire with a 12-volt power source and 5.05 ohms of resistance? So what do we have? We have voltage is equal to 12 volts. And we have resistance is equal to 5.05 ohms. Sorry about my omega there. It's messy. Tools. V, or voltage, is equal to current times resistance. And what do we want? That's going to disappear. What do we want? We want current, right? How much current? So we need to rearrange this tool to solve for current. We'll divide both sides by resistance. Resistance cancels. And now you have current is equal to voltage divided by resistance. You notice something about the relationship between current and resistance? Are they directly related or inversely related? Notice our new tool. Current is equal to voltage divided by resistance. Inversely. So as resistance goes up, what happens to current? It goes down. Keep that in mind. We hadn't talked about that previously, that relationship, because I told you we were going to wait to talk about resistance until next week, what it actually is. I know it's weird to kind of use something in a formula that you don't exactly know what it means, but we do that all the time, right? It's like, yeah, you take things that are givens, or you take things that are constants, and you just use them, not thinking a whole lot about where they came from. So right now we're treating resistance as a constant, even though it isn't. Next week we'll introduce what resistance is, how does it work, how do you make resistance, why do you use resistors. And so we want current. Current is equal to voltage divided by resistance, so 12 volts divided by 5.05 ohms. And so what we're going to get for current is 12 divided by 5.05, which should be 2 and some change. What is it? 2.38. So we have two significant figures here, so we'll present our answer in 2.4 volts over ohms, and then which actually ends up converting into amps as well. So not only do amps equal coulombs over second, but they also equal volts over omega, or over ohms, but we'll get into that.
So should we write that as amps? Or
No, just leave it as that for now. Yep. I would suggest that you leave it as volts over ohms for now. When we talk about resistance next week, I'll demonstrate how amperage also equals this value. So we'll talk about what resistance actually is. All right. Any questions here? All right. And last, what power source is necessary to power an item that requires 2.00 amps with 110 ohms of resistance? So what do we have? What do we have? We know current, 2 amps. And we know resistance, 110.0 ohms, good. And tools, we're going to use the same tool we used previously. Voltage is equal to current times resistance. And what do we want? And now we want voltage, so it's good. Our tool's already in the right form. So it's equal to current, which is 2.00 amps, times resistance, which is 110.0 ohms. Whoa. ohms. And we get that voltage is equal to
Current times resistance.
current times resistance. Yep. 220 amps times ohms. And we'll just leave our units like this for now, because again, we haven't talked a great deal about what resistance actually is. And so when we do, you'll see the relationship between resistance and amperage, and then we can go and figure out how that relates to actual voltage. Okay. So 220 amps times ohms would be our power source. That's the potential difference necessary in order to power this item. All right. Any questions, concerns, things you want to share with the group? All righty. Yes, I would like to keep the annotations. So I will email you